My name is Cedric, and in this demo, we'll be going over how to create well, implement a piano in the FPGA. So, um, the problem that we want to dissect is that um, piece by piece is that we know that we're gonna want a clock, right? Because from our specific clock that's coming from uh, our uh, our FPGA board, which is 100 megahertz, we're gonna be using that clock and manipulating it so that whatever frequency we wish to utilize, we can just like grab it and just like implement it, right? And we'll be using this process by essentially doing a counter, and I'll go step by step on how we're going to be quote unquote grabbing such frequencies. All right, but so starting off, right? Our uh, our main input and outputs, right? Is of course we're gonna have our clock, right? And then we're gonna have an input wire called hush, right? And this is essentially whenever we toggle the button, it's gonna allow uh, the the noise to go off. The noise is just gonna completely go off because the way that's gonna be operating is that once the program is implemented into the hardware of the FPGA, the signal is gonna immediately gonna be starting, right? So and the only way is to turn it off is by pressing hush, right? So and again it's by toggling a specific button that will um, that we laid out specifically to. All right, so uh, hush it's gonna um, make the system go mute when toggled. Okay, and then since we're working with about 16, well, we're working with 16 different frequencies, right? So we're going to be using a 4-bit system to check out each of those frequencies. And then we have our speaker, right? That is going to be a wire. Now, it's going to be a wire because it's something that we're not going to be storing any of these sounds, right? These sounds are going to be varying, and there's not going to be any sort of memory to it, right? So that is why it's going to be an output wire, okay? So first things first, um, I create two different 32-bit uh, values. One is divisor and the other one is counter. The reason why it's 32-bit is because these clock cycles that we're working with, right, that we're trying to generate these different frequencies, right, they're pretty large values, right? So uh, the only way to actually manage these large integer values is to, I think, in order to have one of these largest values that is part partaken in here, I believe you needed like 28 bits, something like that. But of course, we're gonna want. I just wanted a nice number, so I just chose 32 bits. Okay, and then we included another 1 bit uh, for our out, and this out is pretty much going to be assigned to our speaker uh, because we well, we'll go over that. But this out is a specifically it has a specific relationship to the speaker. All right. And what I initially started was because I want to initialize the this register out. I just put a one just so that it's initialized. All right. And these are different frequencies that we're going to be working with. But each of these values are representing the half period clock cycles for the respective frequencies that we're going to be working with. All right. And the reason why it's half period is because We're dealing with um, a clock cycle that is uh, that has a 50% duty cycle, right? So it's going to be 50% on, 50% off, right? And we want to manage both of these, right? And they're going to be both toggling at a specific frequency, right? So um, it's pretty much carrying the load for each half, right? In a sense. So that's what we're working with, half the period clock cycles. Okay. And so this first always block allows us to allows the user, right? Because the user is controlling the inputs of node, correct? So then that would mean that whatever value is being selected from 0 to 15, right? These 16 nodes, uh, from 0 to 15, from our from toggling the switches, right? Our 4-bit switches, it would allow the user to pick any of these uh, any of these nodes, right? And these nodes would then be equivalent to a specific to the register divisor, right? That just grabs that specific frequency that we want, right? And essentially we grab it, right? And then once we grab it, we we then implement a counter, right? And the way that this counter works is rather straightforward than I ever could have imagined, right? So first things first is that we want to be working in pause edge for the clock, right? Um, so whenever it reaches pause edge for the clock, then this is what we're going to start doing. So we're going to look if the divisor is greater than 0, just in case if there's any faultiness, right? But that's the first thing that we want to make sure. And then the second thing we want to make sure before even entering uh, our uh, our clock divider here is that we want to make sure that hush is 0, so it's toggled. I mean, it's not being toggled, right? Because once it's toggled, that means it's going to be a 1, right? And then that's when we would be doing hush, right? But we just want to make sure that that button is not being toggled, so that 1 bit is going to be 0, all right? So going forth from here, right, we're going to be counting, all right? And so this counter is going to be going from 0 to, it's going to keep on incrementing. It's going to keep on incrementing, and then at some point, it's going to stop, okay? And it's going to stop um, in two different predicaments. Two different things are going to happen, right? At one point, the counter is going to match that specific value that we grabbed from the divisor. All right. And once it grabs, once it's equivalent, once counter is equivalent to the divisor, it's gonna out is gonna then invert itself. So it's gonna go from 1 to 0. All right. And so that inversion is gonna allow us to hear that distinction of frequency, right? Um, because essentially that's what you know that's essentially what's going to be happening, right? So we're basically just inverting the signal um, whenever counter is equal to divisor. All right, and when counter is greater than divisor, we want to we want to be able to count again. So then we're able to invert the signal again, so then we can uh, uh, go from high to low and then low to high once more, right? So then that would mean that we would want to make our counter go back to 0, right? And so it's just going to continue in this this loop here, right? It's as simple as it again counting, and then once the counter is equal to divisor, it's going to invert the signal, and then once the counter is greater than the divisor, then they're going to reinitialize it back to 0, all right? And it's just going to be doing just that, all right? And the way that it's being outputted, right, is because this out, right, is from this 1-bit register, right? Because that's all we need. We just need that 1 bit, right? But that 1 bit is being assigned to the output wire that we had above in our module, all right? And that's what it's going to allow us to to output into the speaker. All right, by this assignment here, by using the register, that one bit register, being input into assigned to the output wire there. All right, and so moving on to the test bench here. The test bench is to start off, right? We of course are gonna want to declare uh, our uh, our inputs as registers here in the test bench, as we would see here, and then our uh, uh, output speaker as a wire, right? These are things that we're gonna be wanting to inspect. And moving forward from here, um, we're gonna create our clock, which again we would see that's a 50% duty cycle, right? Because for 5 nanoseconds, it's gonna be 0, and then the other 5 nanoseconds is gonna be 1, right? So it's uh it's split perfectly. And so the way that we're going to conveniently uh um we're gonna conveniently test all the cases, right? Because it's just too many cases, right? We can type them all down, but we're gonna be using a for loop, right? So before entering the for loop, we just initialize note to be the hexadecimal value of 0, right? So that would mean that all the switches are going to be off, right? So that's what all it means, right? And then we'd go forth from here, where hush is just going to be initialized as 1, all right? As a test case scenario, all right? Um, but we would have to we're going to be looking to loop var, and this integer loop var, all it's really doing is just helping us to create our for loop here, um, where we're going to be cycling um, within our 16 different cases, right? So all it's really doing again is that it's just going through the scenario where we're capable of making this noise because this hush bit value is 0, all right, and then we're then able uh, to go over bit by bit with the help of loop var, because now it's being incrementing, and whenever loop var is incrementing, then we're able to choose the specific uh, bit we want to play, right? Since we're working with 16, it's going to be going from 0 to 15, right, for our 16 bits. And then it's going to be testing when we toggle it, all right? And it's just going to be cycling for all the sorts of test cases, all right? And then in here, we're just relating the test bench variables to that of the main source file variables, right? And then in here in our constraint file, we would have our clock of 100 megahertz, and this clock is something that we don't need to toggle. It's already embedded into the FPGA board, and these are our respective notes. Where these notes is going to be um, from the far right. It's going to be the 4 bits from the far right and moving on to the left, right? And then hush is going to be one of the buttons, and then the speaker is specific speaker assignment. Okay. So moving on to showing the implementation here. So when listening to the video, all right, there are a couple things that we would notice is one, whenever I toggled that button on the far left, the system would go silent, right? And when it was not toggled, the system would continue to make noise, all right? So that's one check, right? That we can say that we did correctly. And then when we started our system, it started already making noise when all the switches were down from the far right, 4 bits, right? So that was good, and we noticed that as we switched the values from 0 to 15, we noticed that each of those frequencies were different. They were all unique by themselves. Um, so we noticed that we were able to create our desired frequencies that we wanted to mimic, right? So we could see that our design worked just fine, where we were able to as well implement a hush system if we wanted to mute, right? And so um, this assignment, I actually learned a lot from here. As simple as this main file code here is very straightforward. It was not straightforward to me initially because I guess I didn't grasp my head around an actual counter, and like how we would actually input it. I questioned it very much. Um, but this assignment really helped me uh, actually understand what was actually occurring and get more comfortable into using non-blocking assignments. That's one thing that helped me here. Um, Another thing is just it made me just uh, uh, appreciate this like how the counter is being operated, right? And how uh, there are different ways to manage the counter, and I assume that this counter logic is never going to be going away. We're always going to be wanting to reach out to a specific frequency, so it's something great to learn to know one of the ways that we can implement a counter, and that's really one of the major things that I learned.